A Python ray tracer is quite fast, but it's only running on one core. This is what we are trying to hope for, but this is what we might get. Along the way, there might be race conditions, starvations, deadlocks. Don't worry, I'm here to guide you in this tricky journey. What the bed? It's not because of home quarantine, it's because we are going to talk about a very serious topic in Python, so the serious look helps. Welcome to the sixth part of the Python ray tracing tutorial. In this part, we will not be covering any new ray tracing topics, but we will be talking about parallel processing techniques in Python. Ray tracing is a CPU-intensive algorithm and often called an embarrassingly parallel problem. Why embarrassing? Because if you have 16 cores and 15 cores are not doing anything, then it's a bit embarrassing. Well, imagine that one tiny core crying, "Why me?" A Python program by default runs only on one core. This is true for many other programming languages as well, but those languages have an easy solution: threads. A thread works like calling a function, except that the caller does not wait for the function to return. Both the caller, which could be the main program, and the thread continues to execute separately and independently. Let me show you how this works in C, a programming language so fast that it could be called the Sonic of programming languages. I wrote a short C program that creates 8 threads. Each thread is doing nothing but wasting its time looping until a very high number. When I run this program on my desktop, htop shows that it has created 8 threads. 8 threads were created. Now, each thread is colored in green. So you can see that these threads are all in the R state. R stands for running. Now, if you look at the core utilization, you can see that all the 4 cores are at nearly 100% utilization. Now let's look at the exact same program in Python, but it looks considerably shorter, which is what I like about Python. Now, when we look at htop, you can see that there are still 8 threads and it might look similar, but only one thread is running at any given point in time. All the other threads are in S state, which means they are sleeping. The cores also do not seem to be anywhere near 100%, unfortunately. Threads in Python are like a mixed bag. It's like one day you wake up as Spider-Man, but now you also have the fear of heights. The reason why threads behave oddly in Python is because of the notorious GIL, or Global Interpreter Lock. But before I tell you that, let me tell you what is wrong with threads. Threads in Python share the same memory space as the Python process. This could lead to a weird kind of bug. Imagine 2 employees, thread 1 and thread 2, are busy making pizzas. There is a board in the middle which has a post-it note that says how many pizzas they have made so far. Now imagine both of them made a pizza at nearly the same time. So they look at the count on the board, which is now 7, take a new note, write the number 8, take off the old note and put the new note on the board. Notice that the new count is 8 instead of the correct count, which should be 9. This is called a race condition, or a Heisenberg, which is a cooler name according to me. It could have been avoided if both the threads had read and updated one after the other, instead of doing it at the same time. This bug changes depending on the timing, making it very, very difficult to catch. A common solution for this is to use locks. Now, locks are not a perfect solution. They have their own set of problems like starvation or deadlocks. But it is a very simple solution and it has been in use in other programming languages as well. GIL is just that, one giant lock. GIL is very protective about which thread can access the Python interpreter. In fact, it only allows one thread to execute Python code at any given point in time. GIL exists because Python uses a memory management model called reference counting, which is not thread safe. So GIL exists to prevent your code from blowing up with Heisenbergs. So, if one Python process can run only on one core, why can't many Python processes run on all the cores? This is exactly what Python multiprocessing module does. Now, I rewrote the same program using multiprocessing module. If I run this program, you can see that instead of threads, 8 new processes have been created. And all these processes are in running state. Now the cores are all fully maxed out. Awesome. But here too, we have not gotten rid of Ikson bugs entirely. Sometimes processes need to share a common state like a progress bar among themselves. For this, multiprocessing module provides us a class called the value class. Now, values can be shared between processes. The way a value can be accessed is using an attribute called the value. But before you read or write into a value, you need to protect it with a lock using a with statement. This prevents race conditions. There's a lot more to talk about threads and processes, but hopefully you have got enough background to tackle today's problem. Let's have a look.
Okay, let's start with the subproblem number 6, firing all cores. What's our requirement? Our requirement is to parallelize the ray tracer to use all cores. What does this mean? It just means that I have to use all the cores of my system if it's a multi-core system, and I have to make redesign my Python program in such a way that it uses all the cores at the same time. So we are talking about a really parallel program. It is not trying to asynchronously run things, but it's actually trying to parallelly run things. Now, what about the rest of the requirement? The rest of the requirement is not there. This is pretty much the requirement. This is the point wherein I will stop, or I would ask you to pause the video and try the solution yourself, and wait until you have a working program so that you can continue and then watch how I solve this particular requirement. See you later. So welcome back. Before I go into parallelizing my program, I just want to point out that there was a small bug in my implementation of the ray tracing's ambient lighting calculation, which was pointed out very nicely by a person who goes by the GitHub handle AskHuman. I can quickly show you that if you go to our engine.py and search for ambient, you can find that it used to be color from hex used to be something like this, right? It used to be multiplying with black. This is really the wrong way to do it. I noticed that when I was preparing part 6, but it was a bit too late for that. But if you do this, what will happen is it's multiplying by 0, which essentially gives you nothing. So you're starting with black no matter what ambient color you give. So if you want the ambient color to be used, what I would recommend is to use this fix, to just use white, in which case it should look like this with all FFFF. So there you go. Thank you so much, AskHuman, and just make that fix before you continue. Now on to how we parallelize the program. So if you think about this, you can actually give this parallelizing or using multiple cores a configurable parameter in the command line itself. And that's what we are trying to do here. We'll use a new command line argument called P or -P, which will tell you how many processes, or you could specify how many processes to use. An example of how this could be useful is, for example, you have a quad core system and you want one core for all your essential stuff, like watching, say, a video or something like that, whereas you want the remaining 3 cores to be used for ray tracing. So instead of mentioning to automatically use all the available cores, you could specify a count, like use 3 cores, and you could use the remaining core for your essential work. You should be also having the flexibility of having this automatically set. For example, if you forget to mention this, or if you omit to mention this, the ray tracer should be able to automatically use up all the existing cores. So this is kind of extension of what we already know. we are going to use arg bars here. So I'm going to add a argument here called using the add argument. This time I'm going to use the entire set of options minus. So I'm going to use the long option setting format called processes. I'm going to use action equal to store in small letters. I'm also going to use type equals int, destination equal to process. So let's store the count of processes or whatever the number that the user gives in something called process, in a variable called process. It will be stored as an attribute of the arguments. The default should be equal to 0. Help should be equal to processes. 0 means set it automatically. This should be inside quotes, or else it will complain that variable is not defined. So we are done in defining that, adding that argument. Let's see what to do if that argument is not set. So equal to 0. The classic equal sign mistake, right? So, and the variable called process count. Now, how do we get the number of cores in a system? If you are using multiprocessing, there is already a variable or already a function which can help us do that. From multiprocessing, import CPU count. Great, so we just have to call CPU count. So that you know what it is. Now, if you want to check this, whether it's working correctly or not, there's a very simple way to do that. Just print, right? I mean, use an F string saying that process count equal to process count and return. That's it, easy. So if you don't mention the scene, that's what happens. So as you can see, I gave a process count. I did not give a process count, so it just picked up the process count or the number of cores on my system, which is 4. It's a quad core. Now imagine if I give a process count. So there was a mistake, so glad I'm caught that. So as you can see, this is a default function. This is a good functionality of ArcParse. In case you don't know about ArcParse, this might help you learn more about the different options that ArcParse provides you. So let's go back, delete that and delete that. Next, what I'm going to do is I'm going to remove this rendering part, and I'm going to call render inside this particular file open with block, because I'm going to create something called render multiprocess, and render multiprocess will take care of rendering and writing the file. We'll come to know why we have combined these two different functionalities into the same function in a bit very quickly. But for now, let's assume that both are done by the same thing. Now, you need to pass the process count and the image file. It should be an image file object, so I'm just making sure that it's correctly understood. So I'll save it as an image file object. Next, let's go to engine. And define render multiprocess. So as we know, we are passing the scene, the number of processes, process count, and the image file object. Now I need to use a sub helper function called split range. Let me explain to you what it does. So now the main problem I have is how do I divide the pixels equally? If I have 3 cores, I should be equally dividing it into 3 pieces, 3 parts, so that I can give 3 parts to 3 cores, and if it is 4 cores, it should be divided equally into 4. If I have to visualize this, imagine there are 7 things to be divided. Now I'm saying things because I'm not going to divide them by columns. I'm actually going to divide them by rows. So imagine the height of the image is what I'm going to divide. So in this case, the height of the image is 8. So I'm going to divide 8 rows equally. So from 0 to 7, note that I'm counting 0 here as well. From 0 to 7, I need to divide it equally into the number of cores which I have specified, or the number of processes which I have specified. So here I have specified 3 cores, as you can see in the diagram, and I want to divide this ideally something like this. So I know that if I divide 8 by 3, I'll not be able to divide it equally. I will fall short in the last core. So let me try the best I can. I know that 9 divides by 3 equally, so I'm going to go with 3 each. Or if you actually divide 8 by 3, you should get 2 point something, right? So let's go with the next highest number, or round it up to the next highest number. So let's give 3 to the first core, another 3 to the second core, and see how much remains. So now we just have 2 that remains. So the first core and the second core are equally divided. The third core will be slightly less. This is ideal. I'm very happy with this kind of arrangement, where if there are more than 2 or say 100 cores, all the 99 cores would get the job equally done. Whatever reminder will go to the last core, and that might be a little less, but that core will be able to do the work much faster. So the real question here is, how do we do this programmatically? Before we understand how do we implement that algorithm, you need to understand that there is a built-in function called divmod. It's actually like an arithmetic operator like multiplication or division. In fact, it's division itself, except that when you divide, you just get the quotient, right? But if you use divmod, you actually get the quotient and the remainder. It returns it like a tuple. So the tuple will have two parts. The first part would be the quotient, or the first member would be the quotient, and the second member would be the remainder. So I'm going to use divmod. You can see several examples here. If you divide 11 by 2, the quotient is 5 and the remainder is 1. If you divide 8 by 3, like I said, the quotient is 2 and the remainder is 2. Now we'll talk about split range, which I was just going to use as our helper function. So split range takes a count, which is, like I said, the count of whatever you want to divide. In my case, the number of rows in my image for ray tracing, and how many parts you need. So it'll convert the 0 to count range into parts. And the last part could be, as we saw, smaller than the other parts. So you can see the examples here. If I split range 8, if I give it 8 and 3, I should be able to get 3 tuples. The first tuple should be saying that it's from 0 to 3, and the second is from 3 to 6, and the last is from 6 to 8. If you don't understand this, it's easier to visualize if you compare it to our earlier image. So you can see that in this image, the 0 to 3 is there in the first core. That is our first element in the list. Second one is 3 to 5, which is actually 3 to 6, but because of Python, the way the last number is not counted in Python, so it's exactly what we want. So it's 3 to 6, and 6 to 8, which actually translates to 6 to 7. So this is what we are trying to achieve using our split range helper function. So let me first write it down. It might look a bit confusing, but trust me, it works. Frankly, I got this from Stack Overflow. I don't even remember who wrote it, but if I find the actual credit, I'll credit it to that link. So let's see how this is done. So here I'm going to use divmod for count, paths. So that is split range. Trust me, it works. Next, I'm going to extract different things from the scene, like we do in the render function. We still need the render function, but render multiprocess will also need these variables. It's easier to access if it is locally, and it's more performant that way. Now we are going to use split range. Like I said, we are going to split the height, and that should give us the ranges. Next, I'm going to figure out how I'm going to do this multiprocessing. Now, this is an interesting concept of how do we pass data between multiple processes. Now, as I hinted in the main program, we'll be using the multiprocessing module. Now, multiprocessing module works by creating multiple processes. As we ask how many processes are being created, each of these processes will run in separately and will be managed by the operating system. They are essentially separate Python programs with their separate runtime images. This makes it very difficult to pass data between processes because they all have their process memory space and it's not easy to pass things. Now, if you look at the multiprocessing module documentation, it comes with its own built-in ways of moving information, right, between processes. So you could use queues or pipes, and you could have a third option called files, which is not mentioned in the documentation, but which we can also use. Now, the problem we have is we are having a ray tracer, which will have a lot of pixels depending on how big the image is. A full HD image can have a lot of pixels, which could be very time consuming to pass from one process to another process. Why? The reason is pickling. Anything which is passed from one process to another process using any of the first two methods, queues or pipes, will undergo a process called pickling and unpickling. Now, pickling essentially converts your objects into a binary format that can be shared to another process. Now, once it's received by the other process, it has to be unpickled so that it can be restored back into its original object form, Python object. But here is the problem. The problem is the pickling, the sharing of the information, the unpickling, all these have costs, all these add up, and it actually slows down the program. So why did we use multiprocessing? We use multiprocessing because we wanted to speed up the program. Now, these things will actually slow down the program. So effectively, you might end up with something that is slower than what you started with. So what we are trying to do here is to eliminate those costs. We are going to use some simpler way of sharing this information, or if possible, avoid sharing any information at all. That is what I'm trying to do using files. Now, how am I using files? What I'm trying to do here is, instead of splitting the problem and sharing the information back to the original main problem, I'm going to do the work and store it into separate files. So imagine I'm going to have the entire image split into 4 parts. So the first 25% of the image will go into the first processor, will go to the first process, and that process might be run by the first core of the processor, and it will store the output in a part file. That part file will be stored in your file system. The second processor will do the same thing and store it in another part file. And now all these part files do not have to be shared between the processes. They are all independent of each other. Finally, when all these processes which are created, or like child processes which are created, they are all complete, all you have to do is join these files together and recreate the original image file, or whatever final image file that you want to create. So this involves a bit of trickery in the sense that you have to create a temporary directory, you have to create temporary files, you have to somehow first write just the image header and then write parts of the image file. All these things are possible. I'll just demonstrate to you how it is possible, but it is not very difficult to understand. If you just follow through what I'm trying to do here, you'd be able to understand. So I'm going to create a temporary directory, and for that I'm going to use temp file. So import temp file. Temp file dot mkd temp. Now I'm going to use something called path from pathlib. Pathlib is a Python 3 only module, and it's an awesome module if you have used file paths a lot. I'll be using here mainly to join paths, and it makes it very easy using a join slash operator. But you should check it out. I mean, in case you have to use a lot, if you have to manipulate a lot of file names or file paths, pathlib is really good. So because of that, I'm going to convert whatever temporary directories returned by temp file into a path, and I'm going to create a temp file template so that all the names are easily identifiable. The temporary file names are all easily identifiable. So these are part files with temp extension, and then the processes have to be created in a list so that later I can iterate through them and join them together. Next, I'm going to use a try block. So the reason here is that in case anything inside the try block fails, I wanted to remove this directory. So I'm going to use shutil. So I'm going to use shutil remove tree. So first import shutil. So now we can write the try function where the bulk of the multiprocessing logic will happen. In case anything fails, we know that the temporary directory would be removed, so it's all clean at the end. Whether it fails, so I should change this to finally. Sorry about that. What I meant was whether it fails or whether it succeeds, the temporary directory should be cleanly removed so that there are nothing remaining. Now I'm going to create a new variable called rows done because we need a progress bar. The progress bar is going to be an interesting problem because in a multiprocessing situation, who will actually update the progress bar or who will actually update a global variable which says how many rows have been rendered. Imagine you create a global variable and you ask all processes to increment it. You might end up with what is called a race condition. So we need to be very careful when we are trying to use some sort of a shared value or a shared global variable between processes. And that's what I'm going to do here. I'm going to use something called value from multiprocessing. And value is an integer with a default value of 0. Since ranges contain the rows in height order, so I'm going to call it height minimum and height maximum for all the items inside ranges. So I'm going to give, so you can see that I'm using pathlib very nicely over here. I'm just using a slash operator to join to the directory with the file name. If it was traditional Python or Python 2, I would have used os.path.join, which looks a little more uglier than this. I feel this looks very elegant. Next is how do I get the file name? The file name is just using the template of the file name and passing this number, which is hmin, which I believe will be unique for every part. So if I give that, you should be able to get a full file name, and from temp directory you join that path, so you should get a complete path to the part file. Part file is what the process which is spawned, one of the child processes would be getting as an argument. So I should probably call this processes. So process is coming from multiprocessing. This will be the object that would be representing what process was spawned or what child process is created by this particular program. So it needs a couple of arguments, like what should be the function which should be running inside that process, and I choose to use this render after some modifications as my target. What should be the arguments which should be passed to that particular target, that I will adapt based on what part of the image I'm rendering, whether it is from hmin to hmax, etc. So as you can see, I'm going to use all the arguments that I've used so far as a part of the process. Let us start all the processes. Now at this line, all the processes would start simultaneously, so it will become like a multi-processing program. But the problem is we have to bring them back together. We have to wait until all of them complete. So that is what we are going to do. So we can reuse some of this. Now we have to construct the image by joining all the parts. So before we do this, we need to do some surgery on how we write images. We need to refactor this so that the header part and the rest of the image are two different functions. So you must be wondering why we use static method here. As you can imagine, there is nothing related to this object that we are using here. The width and the height is passed. The file object to write to is also passed. So you really don't need to ask or query the self of the object anymore. So this would be quite important when you don't really have an image file yet, to create the image file. Next, we have to write the image. Now we are going to rewrite the write ppm using these helper objects. So now we have sort of refactored the API. So now we have sort of refactored the API. Notice that we are calling image here instead of self dot. It's image dot. That's because it's a static method. So we are done with refactoring images. So the header is created. So we're again going to use ranges because it helps us in getting the hrmin. It's just a trick to use the hrmin. And how do we get the path file? Of course, we can use the same path calculation here to reconstruct the path to the path file. Now, instead of using the raw function, we can just read and write to this image file. So the final image file is essentially appended by using these parts. It's just bulk copy. This is the fastest way I could find in which you can add or concatenate these parts together. So let's write that. So we are mostly done with the render multiprocess. Now let's refactor the render here. So if you remember, render needs these arguments in addition to the scene. Okay. Now, a very important change here is we do not need to use the entire height of the pixels. We just need h max minus h min. Here also it is h max minus h min. Just to be sure, this is j minus h min. Now to completely redo the calculation of the progress bar, right? So let me add some gaps here. So I'll explain this in a moment. So what is happening here is we are just going to check if there is a variable called rows done. That is an indicator that we want to update the progress bar. We get the lock to the progress bar. This is very important that it's inside a with block, because it's kind of going to wait until some other process releases the lock. This is to prevent a race condition, as we discussed before. And the rows done value is incremented, and it's printed. The progress bar gets printed. Outside the with block, the rows done variable will be unlocked. Okay, let's try to run this. Python main.py examples 2 balls. Okay, so it's saying that this was not a path, so let's fix that. Over here this should be a call to a function. Sorry about that. So it's working, but the progress bar seems to be a bit off. I think I made a mistake here by updating the progress bar at the wrong place. This should be completely shifted to the left. Like we did earlier. Let's try one more time. Okay guys, I think I did a big blunder here. So I should have shifted all these one step to the left. Like this. Or I should say like this. Okay. So I hope I did not confuse you a lot. Again, we have an error. So there was a subtle error here, which I should have noticed, because it was ranging from h minimum to h max. And let's try that. Okay, so it looks like our ray tracer is running fine now. And this would be a bit slower, but we would try a different example outside Emacs so that we can know what the exact performance is. So it looks like the ray tracing is happening correctly. Let's look at the output.
So, how well did we do with multiprocessing? On my old desktop, which is an AMD Athlon X4, which has 4 cores, I ran with 4 processors and almost half the time. So this result actually varies. Sometimes when you run with 3 processors instead of 4, you might get about better performance. This actually varies from run to run or machine to machine. In fact, it actually depends on your OS scheduler, the background jobs you might be running, and the other applications you have. Just for comparison, I ran our ray tracer on DigitalOcean Droplets having 2 cores and 4 cores with Intel Xeons. You can find that having a faster clock speed makes a lot of difference. The last one completes in 2 seconds, which is pretty good for a ray tracer's performance. So, our ray tracer video tutorial series has reached a logical conclusion. This might well be our last part. Many of you had written to me asking for more resources and about topics to cover. So I'm going to show you the topics which I did not cover and talk a little bit more about it. You might be familiar with other ray tracers that initially produce a noisy image and then over time it gets clearer and clearer and produce very realistic images. For example, Blender. This is called a stochastic ray tracer and the concepts are pretty much the same. However, a stochastic ray tracer might produce better results in a very long render time. Many of you have asked me how to implement different kinds of materials and surfaces and patterns. This is something that you could research and play around for yourself. It's actually a lot of fun. Animation should be quite easy. Some of you have already implemented this and you might find the code in the GitHub repository. If you really believe that I should cover any of these topics, please let me know in the comments below. Now, some of you might be thinking, what next? So here are some resources to help you. A book that I really loved both in content and in approach was the Ray Tracer Challenge by James Buck. It has C code, but many people have had successes in porting this into other programming languages, which is the same for our tutorial series as well. If you would like to learn more advanced topics, then I would definitely suggest this book. The Ray Tracing in 1 Weekend book series by Peter Shirley is another great series of books which are short in nature. Again, the code is given in C, but you should be able to implement in other programming languages as well. These books are freely available online. Some of these books actually cover very advanced ray tracing topics like Monte Carlo rendering, so you might find a lot of material there. NVIDIA has also come out with many articles and videos on ray tracing that you might find useful. At the beginning of this series, I said learning a ray tracing project might be worth your time better than a machine learning project. Though I said that tongue-in-cheek, I really felt that while doing a machine learning project, you're actually building, at least in some cases, a classifier that is essentially a black box. Whereas in ray tracing, you actually try to understand the visual perception, how surfaces reflect to light, the physics, the mathematics, and a whole lot of Python. We did not treat anything as a black box, which is why we did not use any third-party libraries, even for reading or writing different image formats. We opened every black box, solved every puzzle together. To me, this deep understanding is what makes a project more meaningful and enjoyable. I hope you experienced that. Thank you.